What is the specific problem that the proposed method, Thermodynamic Natural Gradient Descent, (TNGD), aims to solve in the field of AI training?
The specific problem that the proposed method, Thermodynamic Natural Gradient Descent, (TNGD), aims to solve in the field of AI training is the inefficiency and computational complexity associated with training sophisticated AI models, particularly in the context of second-order optimization algorithms. TNGD addresses the challenge of high computational costs and limited scalability of traditional second-order methods like natural gradient descent, NGD, by introducing a novel approach that combines the strengths of GPUs for auto-differentiation with thermodynamic devices for solving linear systems. TNGD seeks to improve the efficiency of training AI models by leveraging the physical Ornstein-Uhlenbeck process implemented in thermodynamic devices to update parameters based on curvature information of the loss landscape. This method aims to achieve the computational efficiency of first-order training methods like ATOM and SGD, while incorporating the curvature information provided by second-order methods like NGD. TNGD also aims to provide stability and convergence guarantees, especially for ill-conditioned problems, by utilizing the analog dynamics of thermodynamic devices. Overall, TNGD aims to reduce the per-iteration computational cost of second-order optimization algorithms and make them more accessible and practical for training large AI models efficiently.
How does the proposed Thermodynamic Natural Gradient Descent, TNGD method work? Please provide a step-by-step illustration of the algorithm.
The proposed Thermodynamic Natural Gradient Descent, TNGD, method works by combining the strengths of GPUs and thermodynamic devices to optimize second-order optimization efficiently. The algorithm involves a hybrid digital-analog loop where a GPU communicates with an analog thermodynamic computer. The analog computer uses thermodynamic processes as a computational resource, specifically an Ornstein-Uhlenbeck process. The algorithm estimates the solution to a linear system by letting the analog device evolve under the dynamics of the Ornstein-Uhlenbeck process. The analog device settles to an equilibrium state where the mean of the natural gradient estimate provides an estimate of the natural gradient. The GPU computes necessary matrices and vectors using auto-differentiation, which are then uploaded to the analog device. Samples of the natural gradient estimate are taken, sent back to the GPU, averaged, and used to update the parameters. This process can be repeated until sufficient convergence is achieved. The analog dynamics time and delay time are important hyperparameters in TNGD. The algorithm allows for a smooth interpolation between first-order and second-order optimization, providing stability and efficiency in training deep neural networks.
What are the theoretical or practical benefits of using TNGD compared to existing optimization methods like ATOM and SGD?
The theoretical benefits of using thermodynamic natural gradient descent, TNGD, compared to existing optimization methods like ATOM and SGD include the ability to account for the curvature of the loss landscape with a second-order method while achieving computational efficiency similar to first-order methods. TNGD leverages a physical Ornstein-Uhlenbeck process to implement the parameter update rule in natural gradient descent, NGD, resulting in a runtime per iteration scaling linearly in the number of parameters. This allows TNGD to be close to the runtime of first-order optimizers, such as ATOM and SGD, when properly parallelized. Additionally, TNGD offers stability advantages over methods like NGD-CG, as it is guaranteed to converge for any positive definite matrix, unlike CG, which may diverge for certain linear systems. Furthermore, TNGD provides a smooth interpolation between first-order SGD and second-order NGD optimization, allowing for a flexible optimization approach. Practically, TNGD has shown competitive performance with first-order methods for tasks like classification and extractive question answering, demonstrating its effectiveness in real-world applications.
How is the TNGD method validated or tested in the paper?
The TNGD method is validated and tested in the paper through experiments on two tasks: MNIST classification and language model fine-tuning on the Stanford Question Answering Dataset, SQUAD. In the MNIST classification task, a simple convolutional neural network is used, and the performance of TNGD is compared against popular first-order optimizers like ADAM. The training and test losses, as well as accuracies, are monitored to evaluate the performance of TNGD. The results show that TNGD outperforms ADAM, especially in the initial stages of optimization, and also displays better generalization. In the language model fine-tuning task, the Distilbert model is fine-tuned on the SQUAD dataset using TNGD and a hybrid approach called TNGD-ADAM. The training loss for different optimizers is compared, showing that TNGD-ADAM gives the best performance. Additionally, the impact of varying analog runtime and delay times on the performance of TNGD is explored in both tasks. These experiments demonstrate the effectiveness of TNGD in improving optimization performance and show its potential for practical applications in machine learning tasks.
What results were achieved with the new thermodynamic natural gradient descent (TNGD) method in practical scenarios, such as classification and question-answering tasks?
The new thermodynamic natural gradient descent (TNGD) method achieved superior performance compared to the popular first-order optimizer ADAM in practical scenarios, such as classification and question-answering tasks. In MNIST classification experiments, TNGD outperformed ADAM in terms of training and test losses, showing better generalization and faster convergence. Additionally, in language model fine-tuning tasks using the Distilbert model on the SQUAD dataset, TNGD-ADAM, a hybrid approach combining the natural gradient estimate with the ADAM update rule, demonstrated the best performance among the tested optimizers. The analog runtime in TNGD was shown to be a crucial resource, with increasing analog runtime leading to improved performance in both classification and question-answering tasks. Overall, TNGD showed promising results in practical scenarios, indicating its potential to enhance optimization processes in machine learning tasks.
What limitations are mentioned in the paper regarding the proposed TNGD method and its practical implementation?
The limitations mentioned in the paper regarding the proposed TNGD method and its practical implementation include the reliance on the future availability of analog thermodynamic computers, the potential precision issues faced by analog computers, and the need for scaling up the current system demonstrated in previous research. The paper notes that analog computers, including thermodynamic ones, may face precision limitations due to the accuracy of electrical components, which can be mitigated through averaging techniques. Additionally, the scalability of analog thermodynamic computers, although likely feasible using standard electrical components and CMOS-based fabrication infrastructure, still needs to be demonstrated. The paper also highlights the importance of confirming the tolerance of training-based applications to precision-based errors and the need for further detailed studies in this area. Furthermore, the paper mentions the necessity of testing TNGD on a wider range of tasks beyond the small subset evaluated in the current study to determine if the observed advantages hold across different applications.